whether they're coming or.
We were discussing in the room.
Yeah, right.
They might have lost track of time,
Yeah.
I guess.
Should we start with this? Anyway. So thanks for coming. So today we are pleased to have Tomáš Masarík from University of Warsaw, and we'll talk about very exciting Separator Theorem.
Okay, thanks a lot for the introduction. It's a great pleasure to be here. So my plan today is to show you our recent result about finding separator theorem for minor free graphs, in particular in linear time. So this is important, and this is our goal. And let me start by introducing my co-authors. So it's Edouard Bonnet. He's at CNRS and Lyon. Tuka Korhonen, he's currently, I believe, in Denmark, in ITU. Hunkle, he's in University of Massachusetts in Amherst. And Jason Lee, he's from Carnegie Mellon. So those are my co-authors. So let's go to today's topic. And so my plan is to show you the whole proof of the main part. So there are some let's say side parts. I will skip them, but that's at least I believe I will manage. So if you have some questions or anything, please interrupt me. Don't be afraid of that. So let's start by saying what Alon separator. So you probably most of you know that. So you would like to find a subset of vertices such that all the components, if you remove that set, are small. And by small, I mean at most half of the size of the original vertex set. And there is very famous theorem that says that planar graphs have Alon separator of size square root of n. So this size is the size of S. Right? So you can remove square root of n vertices such that planar graphs have Alon separator, such that the rest of the components have size at most n halves if you remove the square root of n vertices, and in particular you can implement it in linear time. And this was also famously extended into KH minor free graphs, and there you can do the same or similar, but with this H, let's say poly H factor. So this will play a big role today. So if we assume that H is small, then you can say that this hides into O, but we don't want to assume that. We would like really to have poly H factor or focus at poly H factor. So in more general graphs, KH minor free graphs, we will have Alon separator of size poly H square root of n, but with a caveat, then this algorithm doesn't run in linear time anymore. So there is this square root of n times m. Okay, so what we will do, we will show how to do it in linear time by completely different technique. So let's go slowly about the statement. So the claim is that we have algorithm that runs in poly h times n. It's part of the running time, and we have two output. We either find Alon separator of size poly h times square root of n. That's what I promised. Or we say false. And by false, we mean that G contains KH as a minor. But output the minor in that time. We just say there are a couple of options. You will see the algorithm later on, and H minor in that time. And in in one other case, we output some different structure. And if you like on that structure, I will show it at least one half. But this is in good time, but it's a randomized algorithm, so It's in poly h time n, but only randomized. Okay, is it clear? The statement should be clear. Well,
So when it says G contains KH minor, that's not probabilistic, right? This is the true statement, but you cannot.
this is true statement.
But you don't output.
We output it some cases, and in the other cases we output something else, which is a certificate. We know that there is KH minor, but if you would like to get the minor model, you have to either run randomized algorithm in poly h times n time, or you need to spend more time to extract the minor out of it. Or we don't know, right? Maybe you can do it as fast by some other algorithm, but only thing we know is that we can do it in the time randomized, or you can spend more time, and then it's easy to extract it. Okay, so let's look at comparisons of results, and then we will jump to the proof. So this table will show you what results were attempting to improve the running time before us. So this is the original result by Alon, Seymour, and Tomáš that I mentioned about. And then if we don't care about having poly h factor, then Reed and Wood already in 2009 had this algorithm that gives polynomial running time, and also for separator. I forgot to mention that. There is also a linear separator size in h, so h times square root of n, but with a caveat that there is some f of h additional factor, and this f of h is some composition of tower of exponentials. So really, if we think then h is some log n or something like that, then this is really not great. But if h is somewhat like constant but not constant, then this is very good separator, and this is in almost linear time. So, and also caveat is that there is not a full version of that yet. There are a couple more results in different directions. So sometimes you can have some trade-offs between separator size and running time. Those are those bunch of results. I wanted to say. So here again, like the first caveat is that this is not square root of n, so it's very nice h, but it's square root of n times log n, and those two are trying to have trade-offs between the running time and separator size. So, for example, this one has nice poly h times n running time, but then the separator size is even worse. Yes, and that's similar story is with this one, which also has separator size larger, but it uses like completely different techniques than the others. So it's like very different approach. And finally paper that I would like to show you today. So we have poly h times square root of n in poly h times n time. So, and it will be simple. I think that's the simplest algorithm out of all of them. So that's big advantage. Okay.
How bad is the polynomial, the degree?
Very good question. So we have degree h to 13, but we haven't tried to optimize it as much. So maybe one can squeeze bit more out of it, but not so much better. So we haven't tried, and we wanted to have it simple, but yeah, it's not like approaching any like very small number like 1, 2, 3. That's not for sure. Maybe not even 5, and then like, but it's not super huge. Like you can, it's like tangible number. Okay, so there are a couple more results, and those are in planar graph directions. So if you look at genus G graphs, then there is very nice result of square root of G times n separator size, and we improved on that as well. So that's a corollary for genus G paper, and one thing that is good, that we don't need the genus, we don't need any genus certificates for that. We will just run our algorithm, and it will, because of KH minor freeness, we will have this good guarantee. So this is just corollary, but we don't need to use it on input. Unlike those other two algorithms, they do need to have it. So that's an advantage. So let me show you our core technique, which is concept of stochastic connectors, and those will be set of trees. So this is like k trees, t1 up to tk. Those will be trees on most of vertices of G. So that the first property says that. So the size of each such tree is most of vertices of G, and most is quantified here. So there, it might miss some of the vertices. We will. This is an important property, and we will address that. But we will have most of vertices. But more important property is the second one. Whenever we take two different trees, so those are those trees Ti and Tj, and we sample two random paths, so one out of each, then the probability path. Oh, I should have said that. So I have two trees. So this is Ti and this is Tj, and I sample two random paths. So maybe this, but the path is to the root. So I only care about path to the root. So in each of them I will select vertex, and I will look at path to the root. So this is P and this is Q. And now the statement is, whenever I do that, then the probability that those paths have some common vertices is at most 1 over 5k squared. So I have small probability, this part, that if I sample random path to the root in one and random path to the root in the other, that those paths intersect.
So when you sample it, do you pick a leaf or do you pick?
I can pick inner vertex as well.
So you just pick.
I can pick any vertex.
Uniformly at random one vertex,
Yes.
and then pick a path.
Yes. I will pick uniformly and random vertex, take path to the root. So it can be in the root. Then my task is easier, because then the chance maybe that they will overlap is even smaller. Okay.
And sorry, your trees are a subgraph of G or unrelated?
Those are subgraphs of G. Yes. They are on. Yes. So first, to get intuition, I will show you this algorithm that we can find in linear time. We can construct KH minor model with probability at least 2 over 5. So I will show you this algorithm. I mean, it's not necessary to show the result because this is, I mean, it was mentioned, but it's sort of set result. But I think it's nice to get some intuition out of it. But I will not show you how to find KH minor model, but I will instead show you almost embedding. So that it's nice concept. I mean, I could look at for some subdivided KT, maybe twice subdivided KT, and it would have worked the same way. But we did it. We used very nice concept of Korhonen and Lochstanov to go via almost embeddings, and I haven't told you what is almost embedding, but the thing is that there is a correspondence that if we find almost embedding, then we can extract KH minor model out of it in linear time. So this, I will instead show you how instead of KH minor to find this almost embedding, which I haven't defined yet, but I will define it on the next slide, and then we will show how to get it. And then, okay. So what's almost embedding? Now you will see that it's quite similar. So almost embedding of H to G. So now I have my graph G, and I would like to almost embed their H. So what I will do? So I have some graph, and I would like to now place there some vertices of H, maybe those 3, and I would like to map edges of H to path in G. Which is the first condition, and second condition is that I would like to care only about edges of H that doesn't share an endpoint. So in this case, if H would be just those H1, H2, H3, and those, they all share the endpoint, so there is nothing more to be shown. But if I have maybe here H4 and this path, then suddenly those two edges, maybe let me pick color, those two edges doesn't share an endpoint, and for those I need that they don't share vertices. So because those paths can overlap, so it's not it doesn't have to be as nice as I draw in the picture. So the paths that are mapped can share vertices, but those that are mappings of H which are non-adjacent, then those cannot share vertices. So they have to look actually as nice as I draw in this picture. And this looks surprisingly similar to the definition of stochastic connector, right? But let's see. So now let's find almost embedding using stochastic connectors.
Actually, I'm a bit confused. Is this almost the definition of the topological minor, or maybe there's
I think the second condition.
second condition because right?
Yeah. I mean it's close. We can replace it by looking at subdivided
So the only
complete
issue is
graph.
like when you share an end, then you can like
Yeah,
set
yeah.
whatever. right?
But you will see where it arises in the proof of how do we find it. So let's try to find it. So first of all, what I will do. So I would like to. I have my H, and I would like to find almost embedding of H in my graph G, for which I have this set of stochastic connectors. So H I have T1 up to Tk, where K is number of edges in H. So let me write it like that. And now what I will do, I will do this mapping random. So this mapping from VH to VG will be random. And now first bad thing that can happen is that okay, and I would like to tell you the intuition. So the intuition is to use, or the strategy, not the intuition, strategy is to use those T1 and up to Tk to construct those paths between those map vertices. So if I have vertex phi u and phi v, then I would like to use this T1 sort of to construct the path. So first bad thing that can happen is that T1 doesn't contain one of phi u, phi v, but this is what is the probability, right? The probability because of the first condition we are missing only small fraction 1 over 10
Okay.
10k. So and now we have 2 endpoints. So this is 2 over 10k, and also we have k edges. So if we use union bound, then this is 1 over 5. So with probability at most 1 over 5, it can happen that actually in all those edges, let me say it again. So because we used union bound over all k possible edges of H, then the probability that we fail, and by that I mean the mapping that we did doesn't exist in the trees, is at most 1/2 overall. 1 over 5, sorry, 1 over 5 overall. So by this we satisfied the first condition of almost embedding, because now indeed those T1 up to Tk gives us connectors. Okay, I haven't told you how I actually I only said that phi u and phi v are in 3. So if I have T1, let's say I have T1, then if I have, here is phi u, here is phi v, then I will take a path to the root from both of them, and then I can shortcut, of course. So this will be the path connecting phi u and phi v in G. So this certifies me that such path exists, and that's the first condition. So for all edges of H, I now constructed path, and now I need a second condition, so that if I have 2 non-adjacent edges, so now let's say this is phi A and phi B, those are non-adjacent, and I have some 2 trees, let's say T1, T2, that now that I don't want them to overlap, at least with high probability. And now,
So can I ask,
Mhm.
so for one edge, the probability that you don't have any tree that covers both ends is at most 1 over 5, right?
no, this is for all edges. Like for one edge is 1 over 5k, because there is k in condition 1 of stochastic connector. So it's like 1 over 10k that one vertex that I mapped is not in particular tree. For both endpoints, this is 2 over
I see.
10k, and then we have k edges. So this
K
k
trees, right?
k trees, and but trees represents edges of H.
Oh. I see. So okay. So H.
Yeah.
Okay.
H has
H is the most K.
yes. So yeah, that was. Thanks for question.
But then, if you have multiple trees having both ends, then do you choose arbitrary? Or? let's
So
say
the other direction, right? First you enumerate the edges of H. So now you choose that edge. I will try to make it with Ti.
I don't understand the question.
No. So for every edge of H,
For every edge of H, I will take three,
yeah,
different tree for different age, and this tree will represent the connection. So it can happen that the endpoints of that age, the mappings of that age are not in the tree.
yeah.
That this is with small probability, like
Right,
1 over 5k, if I have particular edge.
Is there any chance that the endpoint and the two endpoints are in multiple trees?
It's possible,
Yeah.
right? Like most endpoints will be in most trees, but
Right.
that's fine. I will use different tree for different path construction. Like
Different. Oh, I see. So
Yeah.
I see because you
So they
pick
can-
one tree from it.
yeah, the vertices will be in most of them probably, but
Okay.
it's important because of particular path, because at the end of the day I would need to satisfy the second condition
I see.
with high probability, and that's what I will try to do. So I have now two independent edges, which means those four mapped vertices of G, those are the endpoints. Now I look at the connectors. So this is, let's say, T1 and T2. So this is T2. There is phi A, and there is somewhere phi B. And now what I will use the probability property 2 of stochastic connector to satisfy property 2 of the lemma. So I will look at now this vertex to root path, and because phi was originally random, then I will actually satisfy this property. So if I pick, for example, this purple path from T2 and this purple path from T1, then those are randomly sampled paths. Now I use the property 2, right? They overlap only with probability 5k squared. And I have 4 possible choices, right? Because for me it would be bad if this purple path overlapped with the blue path. That would be also bad, like purple path from T2 overlapping with blue path from T1. So in total I have four choices, right? Either purple purple, blue blue, purple blue, and blue purple. So there are like four bad choices for me. So I have to use 4 times property 2 of stochastic connectors. So I have this probability that they will overlap at most, this probability. And now again I use union bound. So how many pairs of edges I have? Like let's say at most k squared half. So this says that the probability is at most 2 over 5. So this is failure probability for the second point. So fail. So in total, I had this failure probability of the first point. This was 1/2. For the second point, it was 2. Not 1/2. 1/5. For the second point, it was 2/5. So in the complement, we have 2/5 probability of success. So this algorithm extracted the through almost embedding with high probability. Okay, it's a sort of very standalone, but I wanted to show it to you to get some intuition about how stochastic connectors works out. But if you missed some details, don't worry, it's completely independent. So the only thing that we will need for the rest of the talk out of this talking is what is the stochastic connector. So I whenever we need it, I will have their definition to recall. But that's I wanted to say that this is from now on the only important thing for the actual algorithm. So this is pseudocode of the algorithm. Don't feel too intimidated with that. I will try to build like alternative algorithm on the board. So let's see what we will do. So the first part is that we would like to run in linear time, no matter what the input looks like. But actually, what can happen that the input can already have n square edges, or like more than. But this is not possible in KH minor free graphs. But that's not how the theorem was worded. So we have this pre-processing procedure at the beginning that if we have two dense graph, then we will not read the whole input even. So we will stop after. If we just care about yes and no, then you can just read the first 100 h squared and edges. And if there is one more, then you say no, this was not KH minor free, and you output no. But if you would like to actually output the model, then you can either use some combination of existing tools and get again probabilistic argument, or we built some procedure that actually constructed deterministically in that time. So that's
Or you can just ignore the remaining input and continue, right? Even if you don't read the remaining edges, you can still find the minor.
yes, but you can also then find the separator and then vote, right? You ignored the edges.
Oh, right.
So if there is still minor, then this is great, but it don't have to be the case always. So this is the first part. I will not show you how we do that deterministically, but it's like, let's say, pre-processing. So from now on we have only linearly many edges. So that's why from now on sometimes, I mean, I will try to delineate that, but if there is n or m, we sort of treat it the same because they are sort of same up to a squared factor. So in the talk you don't have to worry about differentiating edges and vertices of G. Those are roughly the same number. Okay, so then what do we do next? So another important thing is that actually k will be 20 times h squared. So again, we are thinking about poly h. So you can ignore differences between k and h. I mean, it's important for the calculation, but if you don't want to hunt all h's and k's, then just have in mind that k and h are similar and there is, let's say, equality between them. But I didn't want to make mistake of like really changing all k's to h or something. So that's because some statements that are there then easier, but this is really the same. Okay, so now what we will do, we will have like main loop of our algorithm that will try to build sequentially those stochastic connectors. So I will k times build stochastic one tree of stochastic connector, and at the end, if I manage to build all k such trees, then I am done because I know that there is minor and I can use the algorithm that I showed you already, and that's great. Or the algorithm stops at some point, and at that point it stops and returns separator. So that's in this case. I mean, it can also stop and return minor model. It's in different spot, but let me stop in this returning separator case. So the algorithm is done that we are looking for balanced separator of that size. So components are at most that big, but standard thing is to iterate it poly k times, and then this goes below whatever you like. So then you get the balanced separator as I define it. So once this algorithm is finished, if you would like to have better bound separator than this bound, then you have to just run it k times. Okay, so that's why we are looking here for separator of that size. So whenever we find separator of this size, we return. So what we will do in the loop? So basically in the loop we will run a bunch of BFS trees. And more specific on weighted graph. That's big caveat. No, not caveat. That's big. That's important thing. So important thing is that we are introducing some weighting scheme that will help us to find those stochastic connectors, and that's why everything from now will be on weighted graph. So we will have weights on vertices. So the thing in the loop is that we will run we call it KPR, which stands for Klein-Plotkin-Raos algorithm. I will show you it on the next slide. So this is like main routine. They have unweighted version. I mean, it can be adapted easily to vertex weight or so, and it runs in linear times. And this is the algorithm. I will not show you the insights of that algorithm, but this applies BFS H times. So this KPR is a very nice routine, but it's bunch of BFSs, and okay. So now let's look at KPR. So yes. So that's basically our main routine. We run KPR. We either get close to separator. I will say later what KPR is. And in that case, if it's enough balance, then we are done and we return it. And KPR will say that this separator will be reasonably small. That's will be explained on the next slide. And otherwise, we will build one tree of stochastic connector, and we repeat. So, and stochastic connector is just random. Take random vertex and do BFS. But let's first look at. I will return to that. It's not clear, I suppose, at that point. But it will be. I first need to explain what actually KPR is. So now the weighted modification of vertex weighted modification of KPR is following procedure. So first of all, it runs in a good time for us, which is h times m. So which times m, or h times w, where w stands for sum of all weights. So in the algorithm, one thing that I haven't said, at the end we update the weights, and we take care of updating the weights in a way that we doesn't grow beyond poly h times m. So this I will show you this guarantee later, but this altogether will say that we will still run in this time. And what KPR does in this time, it either outputs second point, which is KH minor model, and in this time we will really output the KH minor model in that time, or we will output a separator such that which is of this size, such that the largest connected component, if you remove that separator, is and now the largest is in terms of number of vertices, not weights. Have weak diameter at most this number, but really this number is set up to be at most square root of n. So this number should be leftmost square root of n. That's how we set up delta. And so what this weak diameter is just diameter in G. So maybe we have G. Let me do picture. And KPR finds this separator S such that there is this big component C star which can have itself large diameter, but in whole G maybe it has small diameter because maybe there is some tree like that. So this has small diameter. Is it clear? Okay. So now we know what KPR is. So let's return back to the algorithm. So yeah. So I am now in the stage that I run KPR, and I got this separator ST from this run of KPR, and I will add to my build separator S that I am accumulating over time. And then I will ask, is G without this S already good separator? And then I say, then I output it and I'm done. And because of the size of separator of KPR was this, which is H times poly H not to it's supposed to be in, like, let's say poly H times square root of n size. So it's because of how this delta is set up. So we know that the separator in each iteration is of good size, and then we sort of, if we accumulate all of them together, this is still another poly H times square root of n. So we have a separator of good size, and if we find if it's balanced, then it's good. And if it's not balanced, then we will take arbitrary vertex of this large component C star, and now we will build a tree out of it, starting from that vertex. And we will truncate this tree on the, we will build BFS tree, right? So we take this vertex and we will BFS tree starting from V. So this is another BFS tree. And the thing is that because this C star had small weak diameter, then this tree up to level square root of n will this tree up to level square root of n will see the whole component of C star. It doesn't have to see the whole graph, but it sees the whole component. Okay, and that's nice, because now we already know that this okay. Yeah, let me go here. This is a good stochastic connector, at least in the first with the first property, because we see, because this component C star is sufficiently big, because this is the biggest component, right? If the biggest component is smaller than this value, then we found balanced separator in the previous case, and we were done. So we know that this component is sufficiently big. So now we know that this stochastic connector will see that many vertices, right? So that's because of that. And yes, so then the second point of showing that this is stochastic connector will be, or like tree and stochastic connector will be more complicated. We will get to that. We will not see all the details, but we will get, I hope, close. And this is because how the weights are updated. So Okay. So and for the weights, maybe let me show you the intuition. So for the weights, it's important that we truncate it on this level square root of n, because how we would distribute weights, the thing is that we would like to. So now if you think about BFS3, remember that we have a weighted version of of vertices. So you can think of vertices being really repeated as many times as they have weight. So maybe this was first vertex, it has weight 1, but those long paths, maybe this is just a single same vertex, but think of it as being repeated as many times as it is its weight. Because and still, like, we cut the radius at square root of n. This is important, because now intuition is that we would like to assign, let's say, weight of k cubed square root of n to each level. I will say you in a minute how, but we would like to assign this weight to each level, and we have square root of n levels. So in each step we will increase the weight by poly h times n, because we have square root of n levels. Each level will get square root of n, so this is total increase of weight times n. We have h squared loops, and we have so we will get some poly h times n, and overall size of the weight. Yeah, so there is different way written in the algorithm how we update the weights. So this is how we update the weights, and we will a more precise way. So we will update the weights with respect to size of the subtree. So we will look at the subtree, and now we will count the weight of the subtree, and we will distribute this value based on the size of subtree. So if this is big subtree, then this vertex will increase its weight by big proportion of this k cubed. Like if I look at this size, then this vertex will increase its weight by proportional size of its subtree compared to it. So this is basically more precise way how to write it. So we will add this factor. But maybe for now it's good to have this intuition, just so we will, and you can believe me that this is the same. Okay, so now the proof boils down to showing those 5 invariants, and we basically have weight invariant number 3, because we said that this is the total sum of all the weights is poly h times n, or like k4 to the n. Which I said in each iteration we add weight k cubed to n squared, and we have k iterations, so that's why it's k to the 4. The invariant 5 is very easy because the weight only increases. And then invariant 4 is what we already argued, that the size of this tree is big enough, because this is built on large components. So it remains to basically show invariants 1 and 2. I am afraid that I will not have time to show you how to prove the invariants, but I would like to convince you that this will give us stochastic connection, at least. So, so invariant 1 is actually used in the proof of invariant 2. So we will not need that, but we will need, think of invariant 2. So invariant 2 tells us what's ETV, at the top of the slide. This is an event that random rooted path sampled from T contains vertex V. So then we are interested in this probability for two different trees. What is the probability that they overlap? So if I look at two different trees, how is it possible that they overlap? And we have fairly small probability that this happens. And now the only thing needed for that, so we have this for fixed vertex V, but actually we can take union bound over all vertices. So if we look at over all vertices, we will look at this weight of that vertex, and if we look over all vertices, then we know that total weight of all the vertices is this k to the fourth times n, and we divide it with this k to 6 times n, so we know that this probability is 1 over k squared. So by combination of those two invariants, which is just slightly bit more fancy union bound, we know that this probability that if we take random rooted path in one random rooted path in the other, if they overlap. And it's actually exactly what we want in the second property of stochastic connector. Random path in one, random path in the other. By path I mean always path to the root. And they overlap with probability at most 1 over 5 k squared. So, yeah, I mean, now I am slightly bit tempted to show you the proof of invariant 1 and 2. We have 5 minutes. I think it's like maybe 8 minutes. So I don't. But let me try. Maybe I will show you invariant 1 and invariant 2 could be homework. I mean, once it's decomposed like that, it should be relatively straightforward. So we have what invariant 1 says. So we would like to know the probability that if we take random path to the root, probability that it contains V. So now we would like to look at how we assigned weights. So the probability of this event is at most the size, the proportion of tree below V. So this is this tree below V divided by the size of T, number of vertices in T. Because that's the probability that we will hit V, right? If we sample somewhere else, then we don't hit V. We have to sample below V to hit V, and that's exactly this. Okay, so first of all, we would like to get rid of this size of T, but we know that size of T is almost all vertices, so I could have almost replaced by n, but I can replace it by n half. Like it's definitely more than n half. It's almost n, right? We already know that, so let me do that. And we don't care about constants. So we did that, and now we look at how weights are updated. So weights are updated. Oh, I wrote it here, so we know it, and then we do just algebraic manipulations with that, which is here we have w t plus 1 square root of n. Here we had also 2, and on the bottom we have k cubed and w T. Okay. So now we will use invariant 5 to say that this is somewhat big, and yeah. Yeah, there should have been V here and sorry. So we used invariant 5 that this is somewhat big, like at least 40, and that's what we wanted to show. Yes. So okay, so I have 2 minutes, and I think I will manage invariant 2 actually. So now if we have invariant 1, then we have similar situation in invariant 2, right? We have another tree, different tree. So now those three comes in time. So Ti was older than, let's say, Tt. And this I is smaller, so it was on older tree. So it's important because of the weights. So what I will now, the same calculation holds for the other one. So I will use exactly the same estimate, because the probability that I sample a random path here and that it will hit vertex V is exactly the same, right? It has to lie below V, so the computation is exactly the same, but at the end I will not do this estimation of just forgetting about the bottom part, but instead I will cancel it with the top part. So if I will just repeat it here, then I will have this Vt plus 1 square root of n, and on the bottom I have Wt. But in one of the cases I said that there should be actually smaller t, because this I was at least 1 older than my current time t. So instead I have in this older one, let's say that this one is older, I have here Wt instead of Wt plus 1, because this is coming from this older tree, right? This computation comes from the older tree, this computation comes from the new tree, but suddenly I can cancel this Wt with this Wt, and that's the only that's now my invariant too. I went a bit quicker over this, but it was so close to the proof that I wanted to show you it. Maybe it was slightly bit faster, but this is the trick, that one of the three is older. It has to be, like I sampled 2 trees. So then this Wt is smaller in one of them, and then you can cancel. Instead of this trivial, oh, it's at least 40, and I got, as in variant 2, in this case they actually cancel, and I get this something better, because if by just having twice in variant 1, I would have squared here and it would be too bad. But because they cancel, I have here only Wt plus 1, and this is great. Right, so that's the only difference between invariant 1 and 2, is this slightly more careful handling of this term. Okay, so that's it. Thanks a lot for your attention.
Okay, thank you. Any questions?
Is this argument also applicable for considering KT shallow minor?
I don't know from top of my head. Like we try to think in different directions. So I don't think this particle crossed my mind, so I don't have answer.
Okay. Which results would you want to get?
So, very more precisely, we have stochastics at connector. So we have a lemma that existence stochastic connector implies the existence of KT minor. And I'm wondering that if we have some additional restriction on each tree, for example, each tree has small height, then can we obtain shallow minor of KT? Or it still has a problem that so almost embedding to minor part is problematic.
I mean, we have to have height the square root of n roughly, right? Because sort of we are increasing the weights by that, so by say some square root of n, so don't see how you can make the height of tree small.
But then can we say now we have root tangential minor of kt, or it is also not clear, also almost embedding to kt minor properties problem.
I don't know. Maybe we can discuss it
Thank you.
after the talk.
Other questions? So if you run this algorithm, if I want to get the balance separator, right, then I have to run this k times, right? K or
Yes,
really
yes,
the
yes.
constant times k.
Yes.
Right? Then so what happens? So what is the output if you want to output that result kh minor? Then you output this stochastic connector for certain iteration, right?
Yeah, I mean, whenever you find kh minor, then you can stop. You don't have to iterate.
Yeah, but we actually don't find the kh minor, right? We just,
Yeah, if we don't find, then
I mean, we don't find it. We just get the stochastic.
yeah.
connector,
I mean, in some cases we do find it. If we run kpr and it finds minor, then we get minor.
I see.
So this is like in, but yes, sure. If we get stochastic connector, then we don't get the minor.
Okay. Right. Any other questions? So if not, let's end the speaker again.